we start off talking about antiderivatives and the indefinite integral. There are two topics that are similar, but they're not exact. Capital F is an antiderivative for the function little f. If capital F prime is equal to little f. So f, the capital, is the antiderivative. This is the opposite of what you learn in differential calculus when you take derivatives. If you think differential calculus, this would be the original function, f, and f prime is equal to that. So capital F is the antiderivative. Okay? Let's look at an example. Suppose we have capital F of x equal to x to the fifth. Well, if we take the derivative of this, capital F prime should equal little f of x. And so using the Powell rule for derivatives, the 5 comes around front, times x, and you subtract 1 from the exponent, gives you 5x to the fourth. So capital F is an antiderivative of 5x to the fourth. Capital F equals x to the fifth. There's a really great one, which is one of the reasons calculus is so wonderful. We know that if we have capital F equals e to the x, capital F prime gives us the function little f, and the derivative of e to the x is e to the x. This is why the natural exponential function is so wonderful for calculus. It is its own derivative. But each of these capital F's is just one possible antiderivative for this function. If I have capital F equal to, let's say, x to the fifth minus 7. When you take the derivative of this, you get 5x to the fourth again. If I have x to the fifth plus 7, you take the derivative, you get 5x to the fourth again. So the capital F as an antiderivative is one of many antiderivatives. The same with e to the x. If you add 10 to it, well, when you take its derivative, you still just get e to the x. No matter what you add or subtract to e to the x, it's a constant, and the derivative of a constant is 0. So if you know your original function and you want to find its antiderivative, you have to think about that a little bit, because who knows if it's plus 10 here or minus 8. Now we're going to look at the second part of this antiderivatives and the indefinite integral. And that is that the indefinite integral of little f of x with respect to x represents all possible antiderivatives. So there is one way we can write something that takes care of all those minus 7s or plus 10s or whatever we have when we're looking for an antiderivative. The indefinite integral, sort of an elongated s, of little f of x with respect to x, means dx, that's telling us our variable, is equal to capital F of x plus some constant c. So c is a constant. So when we looked at f of x being 5x to the fourth, the indefinite integral of 5x to the fourth dx is equal to x to the fifth, we saw, plus c. So by putting a plus c to represent whatever constant you have, that means if you take the derivative of all of this, you'll get back to 5x to the fourth. So that the indefinite integral, whenever there's an integral sign, there has to be a plus c. The indefinite integral of e to the x with respect to x, the integral of e to the x dx, is equal to e to the x plus c. Now, there's no way that you yet have a rule for this. We're thinking of this in terms of, if I have capital F of x, and I take the derivative of this whole piece here, I'll get back to little f. And that's all you're expected to do in this first part. Think about if I take the derivative of this, this is what I get. And we'll look at rules for all different possible functions in just a little while. In this segment, we want to look at the basic formulas for indefinite integrals. Now, the formulas are based on how to find an antiderivative. There's a little box in the lesson that says, if the function f of x, little f, is x to the n, then an antiderivative of it is 1 over n plus 1 times x to the n plus 1, where n is our exponent. Okay? But if you want every possible antiderivative, we have to use the indefinite integral form, which means find the antiderivative and then add plus c. The same way here. It'll say in the book, if k is a constant function, if little f of x is equal to k, an antiderivative is k times whatever the variable is. And our named variable here is x. So the antiderivative of k with respect to x is kx. If you want all the antiderivatives, the indefinite integral says add plus c. And so on. This would be the function little f. Find the antiderivative, we get e to the x. Take the derivative of this, you get e back. If our function little f is 1 over x, the antiderivative is ln x with the absolute values, because remember, you cannot take the natural log of a negative number. So this covers whatever x is over here. The absolute value takes care of every possibility. The derivative of natural log absolute value of x is 1 over x. And here, a to the x. We actually use both exponential functions fairly often. The antiderivative of a to the x is 1 over natural log of a, the base, times a to the x. And remember, this a is a number. A is a number. So this would be like 3 to the x, something like that. Remember, you also have to remember your derivative rules, and so the 1 over ln a comes with an antiderivative. We look at the derivative rules along with the integral rules later. Let's look back at the power rule now, because these rules are fairly straightforward, and we will look at those in combination with other rules in a while. Suppose I have a function little f of x equal to x cubed. I could call that little f of x, I guess. If I want to find the antiderivative of x cubed dx, it's pretty clear that this is x to the n power. This is the rule we're going to use where n is 3. So we use the rule for the integral. 1 over 3 plus 1 times x to the 3 plus 1, which would be 4, plus c. So this indefinite integral of x cubed would equal 1/4 x to the 4th plus c. Or you could write it as x to the 4th over 4. Various possibilities for writing these functions. Basic power rule. So that's the way we think of this, like with derivatives. If you take the derivative of 1/4 x to the 4th, 4 comes around front, makes that a 1, and you'd have x cubed. For the antiderivative rule, you add 1 to the exponent and divide. Whereas for the derivative rule, you multiply and subtract 1. Well, let's look at another integral. Suppose I have the indefinite integral of 1 over x squared dx. Now, if you think about those rules for antiderivatives that we looked at, we have x to the n, the power. We have a constant by itself. We have e to the x. We have a to the x. We have 1 over x. This is not the 1 over x rule, but you've only got those 5 rules. It has to fit something. By eliminating the others, it has to fit the power rule. So it has to be written as x to the n, not a fraction. So let's rewrite this using all those rules for exponents that you remember from your past. If it's in the denominator, I can bring this up with a negative exponent. So I now have x to the negative 2 dx. Fits this rule exactly. So this equals 1 over negative 2 plus 1, which would be negative 1, times x to the negative 1 plus c. And since this one started out in the denominator and that looks so messy, we do want to simplify this a little bit. So let's take our negative, and then this x to the negative 1 means write that in the bottom as x to the positive 1. So this is what we've got for this rule. And this is our answer right here. We don't go further. So let's try another problem. Let's go back up. Instead of my x cubed up here, let's look at the integral of the square root of x dx. The square root of x. Well, that's not one of our 5 basic rules, but a radical, a square root, is the same as a rational exponent 1/2. So first I rewrite that as x to the 1/2 dx. And then it fits the rule exactly, so you just follow the rule. This one's a little bit tougher because we've got fractions involved, and a lot of times in our software you keep fractions, so you do need a little practice with your fractions. I want to take 1 over 1/2 plus 1 times x to the, and 1/2 plus 1 would be 3/2. So I'm going to leave it like that for now, and don't forget plus c. Whenever there's an integral sign here, you have to put the plus c on the end. So here I'd have 1 over 3/2. That's the same as 2/3. X to the 3/2 plus c. And one reason I left that as a fraction, because I knew the 2/3 was coming, and that's not a good decimal. It doesn't end. 0.6666 forever. So in a lot of cases where you don't have a neat decimal, we keep fractions because these are exact formulas. There's no estimation involved. Let's look at one more of these. Let's look at that curious function 1 over x dx. Now I say curious because it looks a lot like the one we did that was 1 over x squared. But it's not, it's 1 over x. Well, let's treat it the same way and see what happens. If I bring the x up, since it's x to the first, it becomes x to the negative 1 dx. Looks like it fits the power rule. So let's go 1 over, add 1, negative 1, that's n, plus 1, times x to the negative 1 plus 1 is 0? I don't think so. We can't have 1 over 0. There is no 1 over 0. So that does not fit the power rule. Well, that's exactly why it says n does not equal negative 1. It doesn't fit. It has its own special rule. So that's wrong. What we do with this one, that is a basic rule of its own. That equals natural log absolute value of x plus c. So we went to a lot of trouble to find out. In the end, it didn't work. So do think about, a lot of things are power rule problems, but only x to the first is ln absolute value of x. If it's x squared, it becomes a power, x to the negative 2. We saw that. So be very careful with the power rules, and then realize that sometimes the other ones are a lot simpler, and you simply have to memorize these rules just like you did for the rules for derivatives. In this segment, we're going to look at the constant of integration. Remember that the indefinite integral of little f of x dx is equal to capital F of x plus c. C is the constant of integration. It's what makes the whole function cover every possible antiderivative. We want to find f of x in this problem such that little f of x is equal to 3 and capital F of 1 is equal to 4. So it's very important that you know the difference between capital F as the antiderivative and little f as what we think of as the original function. So we need to find first, find antiderivative of little f. So let's use the integral. Integral of 3 dx. 3, that's a constant. So we have the rule that says take the constant, multiply it by the variable. In this case, our variable is x. And then what we're going to do is add c to take care of every possible antiderivative. And then the second step is use initial condition to find c. Now, our initial condition is that capital F of 1 is equal to 4. Well, this 3x plus c, that is equal to capital F of x plus c. We're going to just use it as capital F of x. Sometimes the notation gets a little fuzzy, so keep track of what you're doing. All of this is what we're going to be working with using the initial condition that f of 1 is equal to 4. F of 1 is 4. So let's go back and use our antiderivative that we found, this 3x plus c. And I'm going to write this as switched, f of x equals 3x plus c, so I can fill in my f of 1. If x is 1, this side is equal to 4, so I let x equal 1. And it gives me an equation to solve. So 4 minus 3 is 1. That's what c is equal to. So my function, capital F of x, that I was looking for, 3x plus c, and c is 1. So we found the initial, we used the initial condition to find the value for c, and we used the rules for antiderivatives to get the 3x. Now in this example, we say find the specific antiderivative for little f of x equals 3 to the x power when capital F of negative 1 equals negative 2. Well, remember what we have. The antiderivative of little f of x dx is equal to capital F of x plus c. Our function little f is 3 raised to the x power. So first we want to find an antiderivative of 3 to the x dx. And then we're going to put our plus c on there and use this as the initial condition to solve for c. This is the rule for a to the x, the exponential function that's just a general whatever the base is. The rule says take 1 over the natural log of the base, 1 over ln of 3, times the function, 3 to the x, plus c. So this is our function capital F of x. So if this is our capital F, we would have, when x is negative 1, we're looking at f of negative 1 here. 1 over ln of 3 times 3 raised to the negative 1 power plus c. Now this looks a little messy. Let's see if we can simplify. F of negative 1 is equal to negative 2. 3 to the negative 1 means move that 3 to the denominator. So I have 1 over ln of 3 times 1/3 plus c. Well, that didn't help a whole lot. Got rid of one of the exponents, though. So let's just see what c is going to equal. C is equal to negative 2, and then this piece subtracts from negative 2. And I'm going to combine those two fractions. 1 times 1 is 1, and this multiplier of 3 I'm going to write in front, 3 times ln of 3. All of that's our constant of integration. Now, there may be types of problems where you'll go ahead and find a decimal value for this, but the answers are just as likely to be left in this exact form. Let's go back up and see how this is going to fit in with our function. Let me get this little piece in the middle out, because I need my function that I got when I took the antiderivative. My function f of x is equal to 1 over ln of 3 times 3 to the x plus c. So all of that goes in plus c, so I'm just going to go minus 2 minus 1 over 3 natural log of 3. So that is my specific antiderivative that has at -1 the value -2. And so this gives me all of this right here is C. In this section, we're still working with the constant of integration, but this is a slightly different type of problem to do. Given capital F of x equals x to the third minus 4, find little f of x, and a condition on capital F that makes the information true. So we have two things. We have to find little f, and then we have to decide which of these conditions goes along with that little f. Now remember, there's a difference between little f and capital F. Capital F is the antiderivative. Little f we think of as the original function. So that if we have capital F, to get to little f, we have to take the derivative of the antiderivative to get back to the original little f. So my derivative here is 3x squared. Rules for derivatives, power comes around front to multiply and you subtract 1. Derivative of 4 is 0. Be really careful with your derivative rules versus your antiderivative rules because you will be using both of them. When I take the derivative, this is little f of x. That is what you can think of as the original function. So we have done this first part up here. We have found our f of x. F of x is 3x squared. Now we have to figure out which of these is correct. Well, this says capital F of 1 has one of these three answers. So we go to capital F. Capital F of x is x to the third minus 4. F of 1 is 1 to the third minus 4. 1 minus 4 is -3. So the capital F that we need for the initial condition is the third one here. Capital F of 1 is -3, and little f of x is equal to 3x squared. So those two parts are what answer the question. Now we're looking at one of our more advanced rules for antiderivatives. We have 5 basic rules for 5 functions. What we have here is a constant k multiplied times one of those functions. And the rule here says that we can just factor out the constant, find the antiderivative of the function, and then multiply the constant back in. It's the same idea as a constant multiplier for derivatives. So let's just look at a few examples. Suppose I have the integral of 2 over x squared dx. 2 is a constant. This is in combination with the power of x. So let's just move the 2 in front. And that leaves us with 1 over x squared dx. 1 over x squared dx is one of the functions that fits our basic formula. I have to rewrite it again as x to the -2 dx before I can use the rule for the antiderivative, which would be the power rule. So I keep my constant multiplier 2, and now I'm going to use the rule for x to the -2, which would be 1 over -2 plus 1 times x raised to the power -2 plus 1, which is -1, plus c. So I can simplify this. 1 over -1 multiplied by 2 gives me -2. And then my x to the -1 here is 1 over x. So this is actually equal to -2 over x plus c. And you do need to be able to do some of these types of simplifications. Now the next example is a little more, maybe not more complicated, but has one thing that looks a little different to it. The integral of 3 times 7 to the x dx. Now when you look at that, I put a big space in the middle. I didn't put a star for times, I didn't put a dot, I didn't do parentheses. In a lot of mathematical software, a space means multiplication. This is not 37 to the x. If it was, it would look like 37 to the x. There would not be any kind of space in the middle. So do be careful when you see things written. If anything looks odd, always ask a question. It makes a huge difference in the way a problem works out. The 3 here is a constant multiplier, so you move it in front. And then we use the rule for 7 to the x, which is the a to the x rule. I keep the multiplier of 3. The antiderivative of 7 to the x is 1 over ln of 7 times 7 to the x plus c. So we could leave it like that. What we could also do, the 3 could go on top in place of the 1, and since the 7 to the x is a multiplier by the fraction, we can just put the 7 to the x on top also. So you may see some strange things when you look at the different questions that you have in our lessons. So just be careful and ask questions. And now this next example is another one that has one little thing about the constant that may be confusing. 1 over 2x to the 5th dx. Looks like the 2 multiplied by x to the 5th, which is true. But remember that this 2 is in the denominator. So what this really is 1/2 times 1 over x to the 5th dx. The 2 is not raised to the 5th power. We can't bring the whole denominator up with a negative exponent. That's what we'll do here next. We'll keep our 1/2 constant, and this becomes x to the negative 5 dx. So be very careful that you don't, from the beginning, bring up and write it as 2x to the negative 5. This 2 is in the denominator, so it's a constant of 1/2 as the multiplier. So the rule for the derivative says, for the antiderivative, keep the 1/2 constant. The rule for the antiderivative here is 1 over negative 5 plus 1, that'd be negative 4, times x to the negative 4 plus c. So here again, we've got some simplifying we need to do. 1/2 times negative 1 over negative 4 would be 1 over negative 8. This x to the negative 4 is 1 over x to the 4th plus c. So if we put all this together, we'd write it as negative 1 over 8x to the 4th plus c. The negative is often just written in front, or it could be written on top or on the bottom. But typically, in front or in the numerator is the way you'll see the answers written the most. Here we have the problem given little f of x equals 1/3 x cubed and capital F of 1 equals negative 1. Find the specific antiderivative, capital F of x, of little f of x. So if it says find an antiderivative, I can use the indefinite integral of 1/3 x cubed dx to find my f of x. 1/3 is a multiplier. I'll write it in front. I'm left with the antiderivative of x to the 3rd dx. Keep the 1/3 as my multiplier. Antiderivative of x to the 3rd power would be 1 over 3 plus 1 is 4 times x to the 4th plus c. So my function I can think of, capital F of x, would be 1/12 x to the 4th plus c, and I'll call this f of x, and you find c by letting x equal 1 and f of 1 being negative 1. So my f of 1 equals 1/12 times 1 to the 4th plus c. F of 1 is given to be equal to negative 1. So to solve for c, I have negative 1 minus 1/12. The easiest way to do this is to get a common denominator. -1 is 12/12. So c would be a -13/12. So the function that I want, my function f of x, is equal to 1/12 x to the 4th plus c, but c is negative, so I'll just say minus 13/12. So this is the function that I'm looking for. Now I can write that as x to the 4th over 12 minus 13 over 12, kind of make it look a little bit similar, but this is fine. In this segment, we're going to look at what we call the sum and difference rules. This first integral that we have here says the integral of little f of x plus or minus little g of x dx. And the rule says that we can split that up just like you did with derivatives. These are antiderivatives. And just find the integral of f of x dx plus or minus the integral of g of x dx. And what we'll see we can end up with is the antiderivative of little f plus or minus the antiderivative of little g plus c. We'll see how we'll just combine both constants into a single constant. So let's look first at the antiderivative of 2 to the x over 3 plus 2x to the 4th dx. Now, according to this, I need to split those up into two integrals. So I have the integral of 2 to the x over 3 dx plus the integral of 2x to the 4th dx. 2 to the x, I have a rule for. That's like the rule for a to the x with a natural log. This 3 in the bottom is a constant. So just looking at this integral, I can pull the 1/3 in front as my constant, and then the antiderivative of 2 to the x is 1 over ln of 2 times 2 to the x plus, and I'll call it c sub 1 because I have another constant to look at. So plus, this is my first integral. My 2 is a constant. I factor it out. I do the antiderivative using the power rule for x to the n. I'll add 1, gives me x to the 5th, and divide by my n plus 1, puts a 5 on the bottom, plus c2. So all of that is my second integral. Now when I combine and rewrite this, looking at the fraction in here and my 2 to the x, 1 times 1 times 2 to the x, and in the denominator 3 times ln of 2. And we'll just leave it like that. I'm going to add c1 and c2 and get another constant. I'll just call c. And in this, I can write that as either 2/5 times x to the 5th, or maybe 2x to the 5th over 5. There are various ways you'll see these written. And I don't need to do any more finding other values for numbers, put a decimal or something down here for ln of 2. This is perfectly acceptable and is the exact answer for the sum of those two functions when we took our antiderivative. Let's look at another example. Find capital F of x given little f of x is equal to 3e to the x minus e to the second power, and capital F at 0 is equal to 4. So I want to find the antiderivative of this function, and then I want to find the specific antiderivative where if I plug in 0 in that function, I'll get 4. This tells me I need to solve for plus c. I need to know what c is equal to. So I set it up the same way I worked the previous example. 3e to the x minus e to the second dx. And since I saw that I can split them up and do them separately, this looks like it's fairly straightforward. No denominators maybe nothing fancy to work with, I'm going to put the answer, go directly to this step and not rewrite them in two separate integrals. So I look at just the first part here. 3 is a constant. Antiderivative of e to the x is e to the x. Minus e to the second is a constant. There's no x here. So that means this right here is some constant. So the rule for the antiderivative of a constant is to take the constant and multiply it times the variable. Dx tells me the variable is x, and then I have plus c. Because I have this initial condition, I now have to use that condition to find the value for c. So let's plug in, if you have x equal to 0, I have 3e to the 0 minus e squared times 0 plus c, so that is my f of 0, equal to 4. E to the 0 is 1. E squared, whatever that number is, times 0 is 0, plus c equal to 4 tells me that c is equal to 1. So my actual function f of x that I'm looking for f of x is equal to 3e to the x minus e squared times x plus 1. Now let's look at an example that's an applied problem. We have some business applications in this segment. First, let's review a little bit. Profit is equal to revenue minus cost. Remember that revenue is income and cost are expenses. To get your income, you have to sell a quantity to people who demand that quantity at a particular selling price. So this makes up your income. Minus your expenses consist of fixed cost, a constant, salaries, rent, etc., and the variable cost that it takes to produce each unit of your product. Materials, wage, employees that work per hour, whatever can vary in a production. So all of this is our basis for what we're going to look at in this section, which are the rates of change of these profits, revenues, and costs. Now, the rates of change we studied in differential calculus. But now we're studying finding the original function given the rate of change. And a rate of change here for these problems would be the rate of change of the function, whatever your function is the marginal of that function. So if we have marginal profit, that would be the derivative of the profit function. If we have marginal cost, that is the derivative of the cost function. That's the rate of change, the profit or revenue or cost in producing and selling one more item. So suppose our first problem is that we're given the marginal cost to produce film. And we write that as marginal cost of Q. Now remember, marginal cost is a derivative, so that is the derivative of cost with respect to quantity. Marginal has to have the quantity as the input variable. So if my formula is MC equals 5 plus 2Q plus 1 over Q. And I want to find the original cost function at the point where the cost to produce one item is $1,000. That's a really fancy film. Well, the antiderivative in general of a derivative is the original function plus some constant. So we want to use that in particular with this application. So we say the antiderivative of marginal cost of the function of the variable q must be dq, because that is our variable, would be equal to the cost function in terms of the variable q. So in this case, it is the antiderivative of 5 plus 2q plus 1 over q dq. So the cost function c of q, I take the antiderivative of the 5. Antiderivative of a constant says take your number and multiply by the variable. The variable is q. It's 5q. Plus 2 is the constant multiplier. Antiderivative of q to the first would be q to the second over 2. Remember, you add 1 to the power. Plus 1 over q, the very basic rule, natural log absolute value of q. And then plus c. Now, because I have a function c of q, I'm going to call my function here capital K to represent constant with k. So this is basically my cost function, and I'm told that the cost to produce one item is 1,000. So c of 1 is 1,000 equal to 5 times 1 is 5, plus, my 2's are going to cancel. 1 squared is 1, plus natural log of 1 is positive, plus k. Natural log of 1 is equal to 0. You may not remember that. 5 and 1 is 6. I subtract 6, I get 994 equal to k. So when I want to find my cost function, after I've taken my antiderivative and I've worked through this, I can find that the cost function, c of q, is equal to 5q plus q squared plus natural log, and I'm just going to say of q, because q must be positive, it's a quantity. I don't really need the absolute values. And my constant k is 994. So this would be the cost function if I want to find the cost to produce 10 items. I'll plug in for q, and then that would give me a dollar amount for my cost, using the fact that I'm given the change and I want the original function.